Okay, now that I found the remote, it was in my hand, and now that we've straightened Donald out, stop it with the steering analogy. All right, with reasonable assumptions, right? When I integrate around a closed curve, I can trade that for an area integral. How do I do that? Like, write down Green's theorem for me.
The integral.
Integral.
With the C on the bottom. Okay.
The C thingy on the bottom,
Yeah.
good. So the circulation around C.
Yeah, P dx plus Q dy equals double integral of the region D of the partial of Q with respect to X minus the partial of P with respect to Y dA.
Okay, perfect. So we can trade the circulation for the sum of the curls around the inside. And we have to remember, because we already screwed this up once,
Sorry.
right? No, it wasn't you. I screwed it up too. Well, okay, it was you. But we have to remember that these should be kind of backwards of the way I would think they ought to appear, right? The Q is the thing that went to Y. It's got an X partial on it. The P was the thing that went with X, and now it's got a Y partial on it. Right? Because really, I'm counting how far off is this from satisfying Clairaut's theorem, this thing about the partials being equal, right? The mixed partial. So what's playing the role of P and Q? What was P?
X to the fourth.
P is X to the fourth, and Q is
XY.
XY. Okay, so to apply Green's, what do I need?
Partial with respect to Y.
Okay, so I need the partial of P with respect to Y, which is 0, and the partial of Q with respect to X, which is Y.
Or say, yeah, sorry.
Right? Okay, and so I can trade my circulation integral over this little funny triangle, right? And I should check positively oriented. Knock it off with the steering wheel.
I wasn't gonna.
So I just want to check, right? Is this positively oriented? However you happen to think about positively oriented. So counterclockwise, if the little guy walking around gets his left hand over the surface, or something about the steering wheel. Cool? However you check me. So I want to apply Green's to this. What do I get?
Well, you get the double integral.
Okay, good. There's definitely going to be a double integral. And for right now, I'm not going to try to figure out what coordinate system to use.
Well, because they're not given one.
Yeah, I'm not given one. I'm just going to write D area, right? So I'm going to integrate over this region, D area, and I'll straighten out what that is in a minute.
And then it's Y minus 0.
Okay, and then the integrand is Y minus 0.
Which is just Y.
Which is just Y. Okay, so I need to double integrate over the region D, Y, the area. And then what's my region D look like?
Looks like, so the first one, you had to evaluate the Y's first. No, I'm not sure.
I don't know. Or the X's first, maybe.
Yeah.
Why aren't you jumping to polar?
It's not a circle.
It's not a circle, nor is it any reasonable part of a circle, right? So clearly we should do this one dx dy, right? Okay, so I'm going to get that this is the double integral of y d, and now you guys get to pick. What do you want to do?
Doesn't matter. It doesn't really matter.
Yeah, it doesn't really matter.
Same
0 to 1.
0 to 1.
How about an order first?
0 to 1 either way.
Well, the outside is going to be 0
Okay,
to 1.
this one's 0 to 1 either way. That's true. Why do we pick one? Let's do the y's first and then the x's.
Okay.
Okay, so if I do the y's first, right? Where do the y's vary from in this picture?
0 to negative x.
They go from 0 to
Negative x. Right?
minus x?
Yeah,
Oh,
because of the line.
Oh, yeah, it's the top.
Right? They don't all go the same height, right? They all start at 0, right? But they go to different y values, right? Depending on how far they are over.
Yeah.
So I need the equation of that line. That line, right, is y is minus x plus 1.
Yeah.
So the y's start at 0 and go to 1 minus x.
Okay.
Cool?
Uh-huh.
So what do you get out of this?
So you get
Well, the integral from 0 to 1
Y squared.
of
Sorry.
y squared over 2 evaluated from
0 to 1 minus x
0 to 1 minus x
dx.
x.
See, sir.
Yes, sir. And so I get the integral from 0 to 1 of
1 minus x squared all over 2.
1 minus x squared, take a 1/2 out,
Okay.
dx. Why would you take the 1/2 out?
Yeah.
It's a constant.
Constant. I'm gonna have to FOIL all this crap out anyway. I'd rather not have to also distribute a 1/2.
Yeah.
So I got 1/2, the integral from 0 to 1 of
X squared.
1 minus 2x plus x squared
Yeah.
dx. So you get 1/2 times
X minus x squared plus 1/3 x cubed.
Evaluated at 0 to 1.
cool, evaluated from 0 to 1,
0 disappears.
which gives me a total of 1/2 times
The third
1 minus 1 plus a third
Yeah. So 1/6.
is 1/6. Cool.
So what did we learn?
Yeah, good. What did we learn?
Steering wheel.
I learned, right, the vector field. There was a vector field here at the beginning. What was your vector field f at the beginning?
X to the 4th and xy. You
Curl
learned
is the
that
same as the line interval?
you learned that you gain energy from.
Yes, perfect, right? I have the vector field x to the 4th comma xy, and I learned that when I go around this triangle, I gain a 1/6 unit of energy.
Which means it's not path independent, is it?
Perfect, which means it's not path independent. Wait, hang on, that was awesome. I actually know something about path independence in terms of Green's theorem.
Well, that would mean that the inside would have to equal 0.
Yeah, right? If I try to apply Green's theorem, right, which asks, hey, when you go around a circle, right, how much energy do you pick up? Well, if the curl's 0, you don't pick up any energy.
Yeah.
You guys see that? So this thing here really is telling you whether or not you're path independent.
Yeah.
Great. Cool.
This is at the
If your
book
double
too.
integral comes out 0, it doesn't necessarily mean it's path independent. It could just be that path was 0.
Yeah, of course, right?
Cool.
If the answer you get out of this thing is 0, that just means that path,
Yeah.
right? That path doesn't have a net gain of energy.
Yeah.
If this integrand comes out to be 0, right, then it doesn't matter which path you're going around. You guys see that? So it's still pretty possible for me to get 0 as an answer, right? Sometimes the circulation will be 0 regardless of whether it was path independent or not. But what I've learned from this inside being 0 is that all the paths have 0 circulation, and that is path independence. Cool.